2 point charges are separated by 6 centimeters in our little example problem. The attractive force between them is 12.2, and you're not used to, it's for newtons in honor of Sir Isaac Newton. It's about 1/5 of a pound. Okay? In America, since we're not metric, we're not used to it. But as the world gets more international, these units, they'll start to click more. Okay? As you learn more about sports and business and all that. Find the force between them when they are separated by 29 centimeters. Okay? In real life, most people are like, whatever, I don't care what these numbers are. Okay? But we want you to try to get a little bit deeper when you're trying to understand how do these touch screen tablets work and all that. It's all about the electrostatic force interaction there. Oh, I pulled up the keyboard accidentally. So anyway, let's take a look here. Okay? So in real life, maybe a good example is screens, okay, for a touch screen, like an iPhone or a Kindle or whatever. So for example, if you want an electric ink particle to stick to a screen, one thing you could do is charge, let's say, the ink positive. Then how could you get it to stick to the screen? Charge the screen negative would be a very simple idea, but in real life it's a little bit more complex. We'll keep it simple, okay? So in the 4-step problem-solving process, step 1 is you always make a little what? Little picture, okay? In this case, it's not that detailed, other than you have 2 charges that are attracted to each other. So what does that tell you? If one is positive, the other one's got to be what? Negative, okay? And the rule is opposites will what? They will attract each other, okay? They'll attract each other with an equal amount of force in opposite directions. Equal but opposite, okay? We're given that the distance between them is 6 centimeters. I'm going to go ahead and label that on my diagram here. 6 centimeters, okay? Then we take those charges and we move them what? Closer or further apart? Further apart, right? So just using purely common sense, what's going to happen to that force? It's going to get bigger or smaller? F2, the second force, will be smaller. In fact, a lot smaller. That's the whole point of this problem, okay? So there's 2 ways to do this problem. One way is with a lot of nasty math, which we could do. It's like setting up ratios and solving for unknowns twice. Okay, I'm going to show you guys the easier way. We're going to do it conceptually, okay? But before we do that, we got to break it down. Step 2, list all of the what? Knowns and unknowns, okay? All we're given is 6 centimeters. That's a measure of distance, which technically we should convert to meters later on if we're going to actually calculate the force using Coulomb's law, but we don't even have to do that, okay? The original force is 12.2 newtons of force, and now we move them 29 centimeters apart, and we want to find out what the new force is, okay? When it comes to understanding electrostatic forces, this fun fly stick toy is a lot of fun here because you can really see what's going on there. If I put some electrons on this stick, and then I put some on the mylar there, okay? Opposites will attract, and in this case, like charges will repel there, right? So it's attracted to my hand because it can be attracted to the positive charge in my hand, and it's repelled by the stick there, right? Because as the electrons pile up there, it's going to repel there, which is why you can get this thing to fly from your hand, there we go, to the stick there. So there's only 2 factors that affects electrostatic attraction. There we go. One is the amount of charge present according to Coulomb's law, and what's the other factor? The other factor is distance, okay? So in this problem, the key is to just realize those relationships there. That if you have too much force, then maybe the ink is sticking to the page too much, or you're wasting battery power. Not enough force, and it doesn't stick to the page at all, right? So when you engineer a device, you're trying to optimize all those factors. There we go. Get rid of the charge on my body by grabbing the sink and grounding myself. So anyhow, the big idea equation, okay, is Coulomb's law, which states that the amount of force between 2 charges depends on an electrical constant K times the amount of charge present over the distance squared. Notice in this problem, they don't give us the amount of charge, Q1 or Q2, and the electrical constant doesn't change, okay? This constant, it looks really weird, but all it is it's a number that's measured in a lab, and you can't change it. It's an electrical constant that to make a proportionality into an equation, you have to have a constant when you graph it out there. See? So all it is it's 9 times 10 to the 9th is what it's measured to be. Newtons times meters squared over Coulomb squared are the units, just to make it work. But don't worry about it. So in this problem, here's what I'm trying to realize, okay? The amount of charge did not change, so this whole top part didn't change. What did change was the what? Was the distance, okay? So the way you can approach this problem without doing a lot of weird math is to realize that the amount of electrical force is really proportional to the amount of charge that you have, Q1, Q2, but it's also proportional to 1 over the distance squared. So notice in this problem, if you compare 29 to 6 centimeters, it's almost 5 times the distance, right? Therefore, the force will not be about 5 times weaker, but what's 5 squared if it's 1 over the distance squared? It's going to be about, can you guys picture this? It's going to be about 25 times weaker, okay? So the key to this problem is we're just going to apply this constant of proportionality right here, okay? If you take the ratio of the distances, in this case, let me clear this all out here. My new distance is 29 centimeters. My original distance was 6 centimeters. So it's almost 5 times further away. It's actually 4.83 in this case. I can't do that in my head, right? But Coulomb's law states that the amount of electrostatic force is directly proportional to the charge, but it's 1 over the distance squared. In other words, if you move something 4.83 times away from something else, the other thing is also 4.83 times as far away. So we have to square that distance, and it's about 23 times weaker. So all I got to do is take my original force of 12.2 newtons, and then is it stronger or weaker as you move them apart? Everybody, it is weaker. I just divide that by 23.36 or whatever, right? So my final answer is it's about 0.522 newtons, okay? So the new force, F2, is almost 25 times weaker. It's 0.522 newtons, okay? So in a nutshell, the way you can approach a Coulomb's law problem when you're not just shoving in numbers directly to plug and chug is conceptually realize that the amount of force just depends on how much charge you have there, but it's 1 over the distance squared. That's the big idea, okay? Practically speaking, most of you guys will not end up being electrical computer engineers as your career choice. That's okay. But a very practical thing is in terms of electrical safety. So for example, you'll probably walk outside one day, right? And it'll be raining, and there might be a thunderstorm, like the past couple of days. So the practical thing is, if you're a tall guy like Brad, you're probably twice as tall as the average, I don't know, 4th grader. If there's a thundercloud over your head, the thundercloud is not twice as attracted to your head because you're twice as tall. It's 1 over the distance squared. You'll be 4 times, okay? If there's a squirrel next to you, you're 10 times taller, you're 100 times more likely to be struck. So it's very important to not be ignorant of how basic electrical forces work in nature, okay? So in terms of electrostatic force problems, it's helpful to be able to apply Coulomb's law in a conceptual format, and that was the goal of this problem.